So in the last class, we were looking at the transmission line, right? And we spent some time on looking at the transmission line equations. And then from those equations, which are the telegrapher's equations, we solved an example. And then we looked at two special cases of transmission lines, which are the lossless case and the distortionless case. And the condition of what is the lossless case and the condition of what is the distortionless case. So distortionless is R over L is G over C. And then we took an example of both of these cases, right? And then we started our next important application of our electromagnetic waves, which is a rectangular metallic waveguide. This was our, say, problem statement. And then what we did is, in first, we just tried to generate a sort of modified boundary conditions that we will require for our metallic waveguide. So we got two boundary conditions. So this was the very generalized way of deriving the boundary conditions. So two very well-known boundary conditions are here. That is, E tangential is equal to 0 and H normal is equal to 0, two boundary conditions. But as I told you, we will require more boundary conditions. We will have more unknowns. So that's why what we did is, if you remember, we substituted in this equation to get this boundary condition, and also in del cross H to get the second boundary condition. So in now we have four boundary conditions in our hand. First is E tangential is 0, H normal is 0, and partial derivative of the normal with the normal space variable is 0, and the partial derivative of H tangential with the normal space variable is 0. Okay, so these are the four boundary conditions that we derived. Now let's go and solve the wave equation and see how the solution for our rectangular metallic waveguide looks like. So let's start. And guys, remember, I will not go into too many details, but I will just, want you to get a feel or understanding of how the problem statement is formulated and how it is solved, and how would it be the electric and the magnetic field components looks like. Okay, we will go through the derivation quickly, but we will not go into a detailed derivation. And remember, in our exams, we don't ask the derivations. So this is just for you to get a flavor of how the wave equations are solved and how the wave equations can get, because in our previous case, we solved it only in one dimension, but here now you will have 3 dimensions. So how do you solve? Just to get a flavor of that. Okay. So let's start. So this is my rectangular waveguide. Now it is a bounded medium. It is not an unbound medium, because it's not an air or free space where your electromagnetic wave can travel everywhere. But now it is a bounded medium. So this is my x-axis, this is my y-axis, and this is my z-axis. So this is my conducting wall, which is my conductor, metal, 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 metal. Inside you have a material of epsilon, and the length of this rectangle is A and the height is B. Okay, so what are we going to have? We are going to have 4 boundaries. If you see here, we are going to have 4 boundaries. First boundary is here, right? Where it is x is equal to 0. Second boundary is here. So which is x is equal to A. So this is the first boundary, x is equal to 0. This is the second boundary, x is equal to A. And this is the third boundary, which is y is equal to 0. And the fourth boundary. which is y is equal to b. So these are the four boundaries that we have where we will apply the boundary conditions. And also we will assume that my A is greater than B. Okay. So let's start. Now, our assumption is, again, my electromagnetic wave is traveling in the positive z direction. So my direction of propagation is positive z. So positive z means what? That is, the wave is coming out of our screen. See here, the wave is coming out of our screen. So we can assume any direction in our analysis, but here we are assuming in the positive z direction. Okay. So my 3D wave equation, remember the 3D vector wave equation that we generated in our the chapter of our EM waves. Remember, this is the one. So it is del square E bar is equal to mu epsilon dou square E bar over 2B. And this is for the magnetic. So this is what we generated without even applying the phasors. Before applying the phasors, this was our equation. And then what we did after this, we put this in, so in rectangular coordinates. So these can be written in the scalar form. So what we did, so this is a 3D vector wave equation. So in the previous case, we changed it into 3D scalar wave equations, where we wrote all these all the components of our electric field and the magnetic field separately. Remember? So this we wrote it as E bar, we wrote it as EX AX plus EY AY plus EZ AZ. So this 3D vector wave equation, from 3D vector wave equation, we got three scalar equations. Three scalar equations, and they are all 3D. One is for EX, one is for EY, one is for EZ. Here also, we did the same thing. We got three scalar equations, or they are all 3D, even including the time, and where we have HX for HY and for HG. So total 6 we got. And then all these 6 equations, guys, if you remember, they all, we wrote it in a form of like this. Remember, del square F is mu epsilon dou square F over dou T square. So we wrote it in a general form of F. And this is my 3D scalar wave equation, where F can take all the field component, EX, EY, EZ, HX, HY, HC. And it is 3D. That's why see, F is a function of X, Y, Z, as well as time. Okay, so this is our starting point here. So we start from here. Now, what we are doing, we are now converting our expression, our wave equation, sorry, this wave equation, 3D scalar wave equation, we are now converting it into frequency domain. So because we want to work in phasor, so that we can eliminate this and we can eliminate the time dependency. So therefore, what we are doing, we are assuming the dependency or a time harmonic of e power j omega t. And therefore, in this case, what I can do, I can write is as del square Fs is equal to, so if I replace this, you will get minus mu omega, minus mu epsilon omega square Fs. So this will be replaced by minus omega square Fs. Okay, so this is nothing but minus k square Fs. So where k is omega root of mu epsilon. So this is my 3D scalar wave equation in phasor form, which I'm now going to solve. Now, next. So as you can see, we have removed the time dependency. So therefore, now my phasor Fs, which is a phasor of F, is only a function of X, Y, Z. And this will represent any of the 6 field components, which is EXS, EYS, EZS, HXS, HYS, and HCS. They are all in phasor. And remember, we can go back to the instantaneous or in the time domain anytime. See how we can do it? We know it. If this is the phasor, then phasor multiply by e power j omega t and take the real part of this, that will give you the instantaneous form. That will give you instantaneous form. Okay. So now let's start. So what we are doing now, we want to now solve our equation 1, which is this one, 3D scalar wave equation. We want to solve. So now to solve this, we have to now borrow some mathematics, whatever we have learned in the differential equations and other things in the mathematics, and we solve this by what is called as separation of variables. So in which we assume that our function fs, which we want to find, is of this form, x of x, y of y, and z of z. And then I will substitute this back in my equation 1. So wherever is fs, I will substitute x of x, y of y, and z of z. So here, this is what I'm doing here. See, so this is del square fs is equal to minus k square fs. Now in place of fs, I am substituting x of x, y of y, and z of z. And then I'm doing some simplification. I'm dividing by x of x, y of y, and z of z. I am getting this as the answer. So which is x double dash of x over x plus y double dash of y over y plus z double dash of z over z is equal to minus k square. And then again, from our differential equation, this above equation, this equation can only be satisfied if each term on the left-hand side is a constant. And therefore, let us equate each of these terms with a constant. So this is how we are equating. So the first term, which is the x term, I'm equating it as with a constant minus x squared. The second term, I'm equating it with a constant minus ky squared. And the third term, I'm equating it with gamma squared. And I'm doing it in such a way that these 3 constants, kx squared plus ky squared minus gamma squared, will become equal to k squared. See, this is on the right hand side. If you bring it on the left hand side, and if you bring all of these right hand terms to the left hand side, and then when you equate, this is what you get. Kx squared plus ky squared minus gamma squared is equal to k squared. And we have just now seen my k is nothing but omega root of mu epsilon. So all this term must be equal to k squared, and which will be equal to omega squared mu epsilon. So this is how we solve it. So this equation is now divided into 3 parts: equation 3, equation 4, equation 5, with a condition of this one, equation 6. And now it becomes easier that the solution of these equations are now easier for us to get. So for example, the condition, the solution of equation 3 and equation 4, where the right hand side is negative, its solution will be a sine plus cosine. So therefore, x of x will be a sine kxx plus b cos kxx. And for this one also, c sine ky by d cos ky by. And here it's not negative, your right hand side is not negative, so therefore its solution will be exponential. And this is very similar to our transmission line equations. Remember our transmission line equation where we solve? So the differential second order differential equation is very similar to that. So therefore you will get an exponential solution, which is either a positive or negative. So e power minus gamma z or f e power gamma z, both are the solutions. And we took each solution independently, individually in our previous classes, whether it is transmission lines or whether it is our EM waves. So this year we are finding the general solution. So we are taking into consideration all of them. So these are the solutions of these three equations. And therefore, my function fs, which is x of x, y of y, z of z, is now this one, which is this part multiplied by this part multiplied by this part. So this is our solution. Now, since as I have told you that we are assuming that my field is, or my electromagnetic wave is traveling in the positive z direction. So therefore, automatically my f is 0. Right? Because this is the positive traveling wave. So my f is 0. So therefore, I have my generalized fs as this one. So here, if you see, we have so many constants. So what I'm doing here, the constant, you also have a constant E, but I'm just absorbing that constant in A, B, C, D. So in general, we have now 4 constants. So if you see here, so here we have 4 constants, A, B, C, D. So these 4 constants we need to find. And in order to find out those components, we will use the derived boundary conditions. And remember, this is Fs. So therefore, this represents all the 6 components of our electromagnetic wave. So this represents all the 6 field components, which is EXS, EYS, EZS, HXS, HYS, and HZS. It represents any of the 6 field components. And what is your gamma here? Gamma is alpha plus j beta, which is my propagation constant, and alpha is my attenuation constant, and beta is my phase constant. Now, this is our next part. So now we need to now go and find these constants. But before finding these constants, let's just talk about what is mentioned here. So if you remember, guys, I told you that in transmission lines, the 2 conductor transmission lines that we saw it in our last 2 classes and we derived, these 2 conductor transmission lines, they only satisfy or they only allow TEM waves. That means they can only TEM waves can exist in this transmission lines. So you can only have, you cannot have your electric field or the magnetic field component in the direction of propagation, because that is the definition of TEM waves. Remember? So TEM waves can only exist in the transmission lines, 2 conductor transmission lines. Now here, when we are talking about a waveguide, a rectangular metallic waveguide. Now inside this rectangular metallic waveguide here, this rectangular metallic waveguide can support only TE or TM. Okay, and here we now don't use the word waves, we use the word modes. They are more or less the same. So they support only TE and TM modes, but not TEM mode. So TEM mode is not supported. Not supported. Okay, it is not supported in our rectangular waveform. Now, why it is not supported, why it is supported here, and why this transmission lines cannot support TE and TM waves, and why they support only TEM waves. Here in rectangular waveguides, why it can support only TE and TM waves, why it cannot support TEM waves. This goes back to the boundary conditions. Okay, this is the most simplest answer which I can give. This simply goes to the boundary conditions, because here the boundary conditions are quite stringent and there are several boundary conditions, 1, 2, 3, 4. So in order for our electromagnetic waves to satisfy these boundary conditions, you cannot have this. So you cannot have a field component in the direction of propagation, whether it is you need to have a field component in the direction of propagation, which is either electric field component or the magnetic field component. So you cannot have both the field component absent in the direction of propagation, which is TEM. So this is what is written here. So the rectangular waveguide, it is known to support the TE and TM modes. And then also the hybrid modes. Remember, we also talked about hybrid modes in our previous classes, where you will have, both your electric field and the magnetic field, both can have their components in the direction of propagation. So this and this, not this and this, it is both the components will have the field component in the direction of propagation. So if you remember, just a quick recap, because we are going to see and we are going to use this. So what do you mean by TEM wave? So in the TEM wave, no E or H component in direction of propagation, right? Now, what do you mean by TE wave? Can anybody help me? Hussein Al-Zaki, can you tell me for the TE wave, what will happen?
Yes, Doctor.
Yes, Hussein. So for TE wave, what will happen? No E component will be there in the direction of propagation, or no H component?
No H component.
No E component, not H component. No E component in direction of propagation. Okay. So for TM wave, no H component in direction of propagation. For hybrid, yes, Mr. Ramzi, can you tell me what about the hybrid modes? Ramzi, you are there? He's not there. Mr. Mohammad Al-Humaydan, can you tell me? Muhammad Al-Humaydan. So you don't have no H and E. No. See, no H and E, Mr. Mohammad Humaydan, no H and E is the TEM wave. See, in the TEM wave, no E or H component. Not all, I would say, I have to correct it. No E and H. So no E and H component in the direction of propagation is for the TEM waves. So for the hybrid waves, yes, what would be the case, Mr. Mohammad Al-Humaydan? Both, yes, this is the case. So if for the hybrid case, both E and H component will exist in the direction of propagation. Okay. So this is the quick comment. Yes. Yes. Thank you. Thank you, Mohammed. So this is the quick revision. 1, 2, 3, 4. Quick revision. So as I told you, our rectangular metallic waveguide supports this. So this is for the rectangular waveguides. They support these. And this is coming from the boundary condition, as I told you, because there are stringent boundary conditions. Because of that, in order to satisfy the boundary conditions, they will have these. And this is for the transmission lines. Okay. So shall we move ahead? Okay. So now what we are going to do here, so we are going to study both. So if you see here, we are going to study TE and TM waves, and the proof why it doesn't support is there in the textbook. You can go and check it. And we will also will not study hybrid modes. We will just study TE and TM. And from here, guys, we will study TE and in more detail, and TM will follow it. So we will just look at the final expressions of TM. So in the TE mode, so let's take the TE mode. So in the TE mode, EZS is equal to 0. Remember, there is no field component of electric field in the direction of propagation. So here our direction of propagation is the Z direction. That's why EZS is 0. So therefore, my transverse electric wave will have only 5 field components. What are those? EXS, EYS, HXS, HYS, and HZS. Okay. Then for the TM case, it is transverse magnetic waves. So therefore, there will not be any field component of magnetic field in the direction of propagation. So therefore, HZS is equal to 0. And therefore, you will have only this 5 field components: EX, EY, EZ, HX, HY, and that's it. So these are the ones. So we need, our objective is to find these components. Okay. So now, how do we find these components? We will find these components. So we are now starting our TE waves. So we need to find EXS, EYS, HXS, HYS, and HCS. We need to find all these components, right? So now we know this is my solution, right? And this solution is for all these 5 components. But before applying the boundary conditions, we need to decide which component I should go and solve and get its answer first. So typically in electromagnetics, we go and we find the component which is in the direction of propagation for TE waves. For TM waves also, the component which is in the direction of propagation. Why this component? Why not these components? No, you can go and you can start with this also. You can make EXS as this and apply the boundary conditions and then get the answer. You can apply this, you can apply this, you can apply this. Why we usually go for this is for a purpose. The purpose is, if we get this component of magnetic field which is in the direction of propagation for our TE waves, then with this component, I can find the remaining 4 components. How? Can anybody tell me? How? By applying Maxwell's equations. Got it? So I don't need to go and get this general expression and then apply boundary conditions and get EXS. Then for EYS, assume this as my general solution, then apply boundary conditions and get EYS. I don't need to do that. That is the advantage of first finding HZS. Because once we find HZS, then the other field components, we can easily get it from HZS by just applying Maxwell's equation. So that's why we go for HZS. So let's start. So let us assume that this is my HZS and it's the general solution which we found. Now our objective is to find A, B, C, and D constants. So let's apply the boundary conditions. So first, if you see here, we are applying the boundary conditions. So let me make it a little bit smaller. So let's apply the boundary condition. So what boundary condition you are applying? So you are applying the boundary condition at this side wall, x is equal to 0. So you have HZS. You're applying the boundary condition to HZS at x is equal to 0. So which is here. X is equal to 0. So this is my x, this is my y, and this is my z. Z is coming out. Now, what is the boundary condition? This is the boundary condition. Dou h t over dou n is equal to 0. Now, let us replace the tangential and the normal for our problem statement. So in the problem statement, the tangential component is the hz component. So hz component is the tangential component. And along which normal space variable? X. Because see, this is the boundary. Remember? So in 3D, it is like this. And my HZ is like this. This is my Y. And what is our normal? X is our normal. This is my Z. So therefore, I'm substituting N with my normal space variable, which is my X, and tangential space variable is HZS. This is equal to 0. And this is equal to 0 at what value of X? At the boundary, which is at X is equal to 0. So now I'm finding the derivative of HZS over X, which is this one. So this is the derivative. And then I will now give X is equal to 0. So I will substitute X is equal to 0. So I'm substituting X, wherever is X, I'm substituting 0. See here? Is equal to 0. Now, when I substitute this, and if I simplify, what is happening? Sine 0, 0, gone. Cos 0 is 1, so A stays. So I'm getting this. So A times this bracket, e power minus gamma z is 0, kx will go away, is equal to 0. So from here, I can say that A is equal to 0. Because this part is our electric field component. So this component, this part cannot be 0. So therefore, this must be 0. So that's why A is equal to 0. Now, if I substitute back in my HZS, I'm getting this expression. So A is gone. So now we have now 3 unknowns. Now, in a similar way, if you also again apply the boundary condition to the bottom wall, y is equal to 0. Okay, this wall. So we applied here at x is equal to 0. Now, if we apply here at y is equal to 0, then you will see that C will vanish because C will become equal to 0. You can do this at home. Okay, you can do this at home. And then we will end up with this expression, which is H0 cos kxx cos kyy e power minus gamma z. So where what I'm doing, I'm putting, introducing a new constant, which is H0. And this constant you can think is as if it is absorbing your constants B and C. So this is our constant. And this constant represents what? This represents the amplitude of my field, which is the amplitude of my HZS. Okay. Now, just a small comment here. So this comment is saying that this boundary conditions that we have applied just now at x is equal to 0 and y is equal to 0. This basically means that at the boundary, the derivative is becoming 0. That means at the boundary, your field will take the extreme values, either the minimum or the maximum. This is the comment which I am writing it here. Okay. So now we have applied to wall x is equal to 0 and to the wall y is equal to 0. Now we will apply to the wall x is equal to A and then y is equal to B. So if I now apply to the wall x is equal to A, so this is my rectangle, this is my x, this is my y, and coming out of the screen is my z. Now I'm applying to which boundary? I'm applying to the boundary x is equal to A. So this is my boundary, which is situated at x is equal to A. So I'm applying to this boundary. So if I apply to this boundary, this is my boundary condition, which is dou HZS over dou x, it's the same, but now I'm applying it at x is equal to A. So therefore, my x is equal to A should be equal to 0. So now if I substitute back here, here is my x, where I substituted A is equal to 0. And now if you see here, we are getting something. Yes, we are getting, say, several solutions here. Okay, if you see here, so this was my HZ. I'm taking the derivative with respect to x, which is this one, and then I'm substituting x is equal to A, which is this one. So now if you see here, again, we apply the same, say, argument that to make this is equal to 0. So these are, let's assume these are gone. So this one and this one should be 0. But this I cannot make it equal to 0 because this is, if this is becoming 0, that means your field is completely gone. There is no solution at all. So therefore, this must be equal to 0. So which is sine kx A must be equal to 0. And now, when can sine kxa will be equal to 0? When the this angle kxa is equal to pi, 2 pi, 3 pi. Yes, guys, because this condition is satisfied for various angles, right? Because sine 180 is 0, sine 360 is also 0. So that's why it is m pi. M pi. And sine 0 is also 0. So that's why if m is equal to 0 here, that means it is sine 0. So where m can take all these values. See, it can take all these values. And therefore, if kx times A is m pi, so kx is m pi over A, where m is equal to 0, 1, 2, 3, and so on. Now, similarly, if we apply it for the second boundary, which is y is equal to b, see here. So first find the derivative of this with respect to y, and then substitute y is equal to b. Then what you will see, again, you will see similar thing, which is, this is becoming 0. So out of these, this one becomes 0. So therefore, kyb is pi, 2 pi, 3 pi, or n pi, where n is equal to 0, 1, 2, 3. So therefore, ky is n pi over b, where n is 0, 1, 2, 3, and so on. Got it? So now you can see we are getting several solutions when we change n or when we change m. Okay, so we are getting a complete, 180 degrees. We are getting 360 degrees. 180 degrees means what? 180 degrees means one complete cycle of sine wave, right? Then 360 degrees, 2 complete cycles of sine waves. We are getting these. Now, what we did, once we got kx, once we got ky, and remember one thing, yes, m can take values from 0, 1, 2, 3, n can take values from 0, 1, 2, 3, but both of them cannot have 0 and 0 together. Okay, both cannot be 0 at the same time, because if both becomes 0 at the same time, again, if you substitute, then your field will vanish. That means your field cannot exist. So it cannot be. And we will see it later as well. So now we got kx and we got ky. We already have this equation, remember, from our previous discussion, which is kx square plus ky square minus gamma square is equal to k square when we use the separation of variables. So here, if I substitute kx and ky, which I obtained here, ky and kx, which I obtained here, then I can substitute kx square is m pi over a square, ky square is m pi over b square, and from here I can get gamma square is m pi over a square plus n pi over b square minus omega square mu epsilon. So what is happening here, guys? So if you see here, if you see the field, yes. So this is my field expression. See here. So this is the x component of not x component. This is the part of my field component, which is a function of x. This is a part of my field component, which is a function of y. Now, if you see here, kx is m pi over a and ky is n pi over b. So what are these two telling us? These two are telling us that my magnetic field component Hz, if this is my x, this is my y. So it is telling us that, and this is z. So it is telling us that my magnetic field component Hz, if I move along the z direction, if my magnetic field component, if it moves along the z direction, it will move and it has to satisfy this condition. It has to satisfy this condition. That means it should be something like this. Sorry. So it should be something like this, right? So pi, or it should be something like this. And it is restricted. It cannot go further. See, it cannot go further. So there is no traveling in the x and y direction because the boundary conditions are stopping here. See? So you can only have 1 cycle or 2 cycle or 3 cycle and stop. That's it. And in the y direction also, it's a similar thing. See, in the y direction also, and then it is the superposition of this, which will form a sort of 3D pattern here. And that 3D pattern is your HZ. And this 3D pattern will be traveling along the Z direction because of our propagation constant. So it's a little bit complicated, I understand, but we want you to just get a flavor of how it is happening. And that's why you are getting so many patterns, because every combination of M and every combination of N will give you a different sort of pattern of your HZ field. Got it? So now let's continue. So this is called as gamma. And now, as I already told you, okay, I think it's time, guys, just give me a minute. So as I already told you that our rectangular waveguide works as a high pass filter. It cannot allow all the frequencies to pass through it. So this is what we are now trying to see. That means below which frequency your rectangular waveguide cannot pass the electromagnetic wave, below which frequency. This is what we are trying to see. So we are defining a frequency at which gamma is 0. Gamma is 0 means that there is no propagation constant. That means that is the frequency which cannot exist in the rectangular waveguide or cannot propagate. And that frequency is called as the cutoff frequency, FC, which is omega c is 2 pi FC. Now, if I put gamma 0 and make this omega as omega c, and if I simplify it, I will get the cutoff frequency, which is 1 over 2 root of mu epsilon root of m over a square plus n over b square, or FC is u dash over 2 root of m over a square plus n over b square. What is u dash? U dash is 1 over root of mu epsilon, which is the phase velocity of the unbounded medium, okay? Of the unbounded medium without the conducting waves. And m is equal to, and n is equal to 0, 1, 2, 3, but both cannot be 0. So this is the cutoff, okay? So I think we will stop here, guys. And in the next class, we will look at some of the examples, and also we will try to look at the transverse magnetic wave. Okay. So anything else you want to ask?
Doctor, will you do a 5th quiz?
No, we already discussed about this, right? We already discussed that I will have only 4 quizzes because of the shortening of the semester.
Can we have optional quiz to have a better grade?
We have
I have already helped you guys, right? I have already taken the best 3 quizzes.
I mean, the scale, doctor, is not doing any difference. I mean, the scale is up to 9.5, 9.8, 9.9. So,
yeah.
While the average is 4.5.
So why the average is 4.5, Sultans? This is the performance. I can't do much, but yeah, from my side, the help that I can do, which I already, told you that I will push the highest student to the maximum value. But for the 5th quiz, I remember we already discussed, because of the shortening of the semester, we will not take one more quiz.
I mean, it's optional to pick the best of 3 out of 5.
No, Sultan, please.
Okay.
If I'm taking an optional quiz, then I will take best 4, not best 3. Because this is what we agreed in the starting of the semester, that I will take the best. If I take 5, then I will take best 4. If I'm taking now 4, that's why I'm taking best 3.
I think this is fine. You can
give one more quiz to you, then I will take best 4. Okay, I cannot eliminate 2 quizzes. 2 quizzes, eliminating and taking best 3. I don't think it would be appropriate.
I think this is fine to do 5 quizzes and taking best 4.
Okay, if this is the case, let me look at it, because I cannot, yeah, I cannot promise you, because of the shortening of the semester. You know, we are doing our best, and unfortunately our exam is the very next day of the last day of class. You know it very well, right?
Yes.
Yes, so that's why, you know, the other sections and my sections, we are trying our best to finish our syllabus by 22 April. We want to finish by 22 April. We don't want to keep any class on 25th. We don't want to keep it, because we want to finish by 22, so that we want to give enough time for the students to prepare for the final exam. Okay, so I will look at it. If optional quiz, because definitely it will be an optional quiz, I can look at it, but it provided if I can finish, because you guys know very well, if I take a quiz, 20 minutes will be gone. So I have to look at it, whether I would be able to manage the quiz and complete it by 22nd of April. Okay.
Okay, thank you.
Thank you.
Doctor,
Yes.
can I meet you after the class?
Sure, no problem. Just you can directly come in the office hours. I'm opening my office hours. Okay.
Okay, thank you.
Okay. Thank you very much, guys.